Excellent. Wonderful. Okay, 5, number 7. You know, sometimes if students are just looking at this, the limits of integration would upset them, I think. Just seeing this natural log of the square root of 3 over 3, they'd be like, this is not going to end well. But it's all fine. A lot of times things look a lot more complicated than they are. Okay, actually, this one, I'm going to see if I can remind you. I think I did one very similar to this in class yesterday. Did you see it in your notes? I mean, I will absolutely go over it now, but it was example 22. So similar idea, but I'm going to go through it again because I'm sure it will be helpful to see it again. But it's like example 22. Okay, so the big difference here, spotting the difference between a general U substitution and the inverse tangent would be the fact that you have e to the 2x in the denominator. If you took the derivative of that, you get 2e to the 2x, and you don't have e to the 2x up here in the numerator. So right off the bat, you should not be thinking about a general U substitution. You should be thinking about an inverse tangent function. I'm going to make this a little bit easier for myself by pulling out the 11. You don't have to. Personally, when I see something that looks like an inverse trig form, I just like to see it by itself without any other things in the way. So the 11 was annoying me, so off with the 11. So we're thinking that this is the form of an inverse tangent of u, which, if you'll remember, is du over 1 plus u squared. Another thing that's sort of keying me off to this is the fact that you're seeing the square root of 3 over 3, which is actually a special angle value. Like, for instance, I know that the tangent of pi over 6 is root 3 over 3. So that's another thing where I'm like, wait a second, this is not just any old irrational number. This is a special angle value. So same note that the tangent of pi over 6 is the square root of 3 over 3. So that's another thing that's hinting you to the fact that this is leaning in the trig direction. Just a few things right off the bat that kind of are making me think trig. So if you're going to do this, you can rewrite this again, and I should have done this here. If you rewrite e to the 2x as e to the x quantity squared, I think that you can match this up a little bit easier. So it's just another one of those situations where it looks really confusing at first, and then if you just do a little rewrite using algebra, now you can see that it's in the form 1 plus u squared over u prime. So if you let u be equal to e to the x, well, of course, then u squared is e to the x squared, which is also known as e to the 2x. du is e to the x dx, which is excellent because that's what we've got. So there's your du, and we have u. So we're going to go ahead and rewrite this. The nice thing is I've already got a 1. That's one thing that we look for with these inverse trig integrals. We try to make this constant in the denominator 1. We already have it. So there's not even a whole lot more we have to do at this point. We will switch the upper and lower limits of integration. We might as well go ahead and do that. So we have x equals 1 and x equals the natural log of the square root of 3 over 3. And we just said that u is e to the x. So that means that u is e to the first, which is just e. And u is e to the ln square root 3 over 3. And that just means that u is equal to the square root of 3 over 3. Okay, any questions here? Wonderful, wonderful. Okay, let's get this rewritten in terms of u. Don't forget we still have this 11 in front. 11 is such a weird constant multiple because it's just not that recognizable. It just looks like vertical lines. And then we're going to go from u equals root 3 over 3 to e. And our integral is then rewritten in terms of u as du divided by 1 plus u squared. Oops, running out of space. So this is 11 times the inverse tangent of u. And that's going from the square root of 3 over 3 to e. And if you're like me, you're probably looking at this e thinking like, wait, did I do something wrong? Shouldn't that be a 1? Because I guess in my mind, I'm thinking like inverse tangent of 1 would actually give me an angle. Inverse tangent of e doesn't. That doesn't necessarily mean that it's wrong. You might just have an exact answer here that you can't actually write in terms of some special value of pi. So this is 11 times the inverse tangent of e minus 11 times the inverse tangent of the square root of 3 over 3. And we already stated up here that the tangent of pi over 6 is the square root of 3 over 3. So this quantity is going to be pi over 6. So we'll rewrite this as 11 inverse tangent e minus 11 pi over 6. And that is going to be the exact answer. Okay. Questions on this one? Yeah, and like I said, sometimes when these answer forms are kind of weird, it makes you think you did something wrong. And in this case, this is the answer. It doesn't mean it's wrong. It just looks different than some of the other answers that you've obtained in your life.
Can you do number 2, please?
Number 2. Let's see. Number 2 on the 5-5 homework? Okay.
Yes.
All right. And then Morgan wanted 50 on the review. All right. Let's see. Yeah, if there's anything you guys want to see, just start entering it in the chat, and then I can go through the chat and we'll kind of pick our way through it. Don't feel like you have to wait for me to get through someone else's question before you ask. We can just set up like a running queue of questions. All right, number 2. So this one is find the definite integral. We're going from 0 to pi over 4, and we're looking at the sine of 2x divided by the square root of 5 minus 3 times the cosine of 2x dx. I'm sure I copied that down right. So the only numbers that iterate in this problem are the 5 and the 3. So anyone else should have had one that was really similar to this one. Okay. Now, it's possible that you would look at something like this and maybe think that it looks like it could be an inverse sign because you're seeing a radical and then you're seeing a constant minus some function of x. However, this function is not being squared, and you can't write the 2x like it's being squared like you can with e to the 2x. It's not the same. And also you would note that the derivative of negative cosine is sine. So your derivative is actually sitting in there. So this is going to be a standard u substitution. Oh, and by the way, oh yeah, it looks like you guys are specifying. Yeah, so if you're specifying a problem you want to go over, make sure you tell me if it's on where it's from. So yeah, test 5, review number 12. Okay, final review. Yeah, make sure I know where it's coming from. I don't want to do the wrong one. Or if it's from the 5-5 homework. All right, so if you're not sure what else to do, you can let your radicand be u. That's where I would go, not the full denominator. If you let the full denominator be u, you'll end up in a big mess because of this derivative. But you can let u be 5 minus 3 times the cosine of 2x. And by the way, the parentheses on the 2x are non-essential. Include them if you want. Don't include them if you don't want. Web of Science is very funny about when it does and doesn't. It's kind of random. The derivative of u, well, the derivative of 5 is 0. And the derivative of cosine is negative sine. The derivative of negative cosine is positive sine. So you would have positive 3 sine 2x. And don't forget to chain on the derivative of the inside function. So that gets multiplied by the whole sine function. And by the way, you can always work your way backwards and make sure that this function ends up working your way in reverse as the derivative when you're done with it. Burfin, go ahead.
I took the antiderivative of it, so I got like 5x, like minus, that's why I got it wrong. I see.
Okay, so you don't have a question on it anymore. I'll still finish it. Maybe I'll just do it a little more quickly than I would have, just in case someone's like, ooh, I was going to ask that too.
Thank you.
Since I already started it. Yeah, but that's very common. Like I said, when I teach Calc 1 and Calc 2 at the same time, sometimes I just go the opposite direction because you forget which way you're going. Okay, so the derivative is du is 6 sine 2x dx. Wonderful. Okay. Now, we'll go ahead and say we have 1/6. Sorry, my mind just blinked because I just realized that I totally forgot to set the Olympics to record. And like, I was really looking forward to this. So I might have to make my husband do that real quick, but I'll finish this problem first. Priorities. Okay, I'm going to rewrite this as 1/6 du over the square root of u, but first I'm going to change the upper and lower limits of integration. U is 5 minus 3 cosine 2x, and twice pi over 4 is pi over 2. The cosine of pi over 2 is 0, so u is going to be equal to 5. 5 minus the cosine, 5 minus 3 cosine of 0. The cosine of 0 is 1, and 5 minus 3 is 2. And if you guys see me do anything weird that doesn't make sense to you, let me know. Maybe it's not weird at all and it just looks weird to you, but maybe I'm doing something weird because, I don't know, who knows. Okay, I'm going to put the 1/6 out front, and then I have a du, and that's going to represent my numerator. and then divided by the square root of u. And then we'll rewrite this as 1/6 times the integral from 2 to 5 of u to the negative 1/2 du. Increase the exponent by 1 and you'll get positive 1/2. When you divide by 1/2, you multiply by 2. U to the 1/2 is the square root of u. And we'll take that from 2 to 5. And that leaves us with 1/3 times the square root of 5 minus the square root of 2. And you can distribute that if you'd like, or you can leave it. Okay, I'm going to text him real quick. So sorry. Please record the Olympics for me. All right. Excellent. I could probably do that from my phone, but it's real iffy. Okay. Any questions on this particular example or homework problem, I should say? Okay. Let me see what's next. Number 50 on the review and number 21 on the review. Okay, because I screwed up these numbers, just to save time. Mine, I want to make sure I have the right one. So 50 that was the average value one, Morgan? No, wait. I'm supposed to subtract 4, right?
It's from like the blank, not like the key, but the blank one is 50 and then 21.
Okay, gotcha. I should pull up the blank one because then it will be a lot faster for me to figure out which one you're asking me about. Let's see. Final review. It might be on this computer somewhere, but I don't know. I can't find it quickly, so I'm just gonna download it quickly. It's found. There we go. Okay. Number 50. Oh, okay. So this is an integral. So this is 1/2 to 2, 1 minus 1 over x squared dx. This is the one, right?
Yeah, that's right.
Okay. Awesome. There's also like a test 5 review, but you did specify, oh, you said review guide. Okay. This one. Wonderful. Okay. So with this one, we don't actually need to use a u substitution because we don't have any like specific function of x that is a composite function. So we're going to go ahead and use the FTC the way we normally would, but I'm just going to rewrite this one more time so that we have x to the negative second power. So we can use the power rule when we integrate. So for the first term, we're going to get x. And for the second term, we're going to increase the power by 1, which gets us to x to the negative 1. And then we'll divide by the new power. But I kept this minus sign there. And then when we divide by the negative, we'll end up switching that. And since we did not use a u substitution, everything is still written in terms of x. We're going to keep those original limits on it. So now I'm going to rewrite the antiderivative as x plus 1 over x. So the x to the negative first will now go into the denominator. And then dividing by negative 1, we'll just switch the value of this sign. And that will go from 1/2 to 2. And we'll evaluate at 2. and subtract off the antiderivative evaluated at 1/2. So this will be 2 plus 1/2 minus 1/2 minus 2, because 1 divided by 1/2 is multiplied by 2 in the numerator and denominator, and you'll get 2. And then 2 minus 2 is 0, and 1/2 minus 1/2 is also 0. So you should be getting 0 for the value of this limit. I think if I add 4, oh, this is 55 on here. I don't know how my, it could be that my key is like from a completely different review guide that I used a different semester. I don't know, but it should say 0 on your key. Go ahead, Isabella. What's your question?
So you said not to use substitution when?
So you don't need it if you don't have some sort of composite function. So for instance, if you can rewrite this, like which you can do as just x to the -2nd, then you don't actually need a u substitution. When you would need one would be, for example, let's say you had something like, I don't know, 1 minus 1 over x plus 1 squared dx. This would be a situation where you would need to do a u substitution. You could let u be x plus 1 and du would be dx. And you could split this up into 2 different integrals and just do each term separately. Obviously, this term wouldn't need a u substitution, but this one would. And there's really no other way to do this, because even if you expanded out the denominator, you would be stuck because you wouldn't even be able to evaluate it that way. So you would have to evaluate this as 1 over u squared. So what you're looking for here is some sort of situation where you have an inside function. And here you have an inside function, like a quantity that's being taken to the 2nd power, whereas here, there's really no inside function other than x. There's no composite situation. So that's why you don't need a u substitution here. Is that clearer?
Yes, thank you.
Okay, you're welcome. Okay, so that was 50. She also wanted to see number 21. Find that. Okay, so this was about continuity. So this is a great one to go over, just because even though summer classes are so short and technically this wasn't that long ago, it's shocking what we forget in such a small amount of time. I'm going to label these so everything gets put in the right order. Right over there. And I'll post these notes also, just in case you were wondering. Okay, so this is number 21 from the review. This is f of x equals x plus 1, or 1 over x. One of them is for x being less than 1, and the other is for x being greater than or equal to 1. And you're asked to determine points of discontinuity and then state the type of discontinuity and whether the function is left or right continuous. So one thing you can do to automatically show that the function is not continuous is to just evaluate the function at these points where you have the breaking point, and that occurs at 1. So at 1, it's like this boundary. I think that's how we referred to it in class. You could also graph it. You might have an easier time actually graphing it, just because I feel like a picture says more than actually evaluating the function. But if you did, okay, so we're really going to be focusing on x equals 1 is f of x continuous there. And the reason we only care about what happens at 1 is because we already know that the function x plus 1 is continuous on its entire domain because it's a polynomial. This is just a line with a slope of 1 and a y-intercept of 1. The function 1 over x is also going to be continuous on its entire domain, and its domain includes all real numbers that are not 0. However, this function is only valid when x is greater than or equal to 1, so 0 is not even included in this piece of the graph. So this function will be continuous from for any value of x that's greater than or equal to 1. So we already know that these are continuous on their own. We just need to know what happens at that boundary line where that change occurs. So if you were to actually evaluate f of 1 at both of these points, and yes, I know technically if you evaluated f of 1, that's not really a function value here because you're only evaluating it for values that are less than 1. However, this would be the value that your function's approaching. So f of 1 would be like 1 plus 1, which would be 2, or f of 1 would be 1 over 1, which is 1. So evaluating it for each instance, well, 2 does not equal 1, so automatically you know it's not continuous. If you feel comfortable with this, you can do that. If you feel like you need to see this visually, then graph it out. We said that this was a line with a y-intercept at 1 and a slope of 1. And this is valid for values of x that are less than 1. So like, for instance, if x is 1, we said the function value is 2. However, we have to leave the circle open there because we can't actually be equal to 1. So we're only going to be able to approach it. But if x is 0, y is 1. Did I say that? No, yes, 0. If x is 0, y is 1. Sorry. If x is 0, y is 1. I'm so used to the boundary being on the y-axis. Sorry that I automatically put it there when it shouldn't have been there. F of 1 is 2, not f of 0. Leave it open. F of 0, where this function corresponds, is 1. F of negative 1 would be 0, and you can kind of see now how the slope just takes you down and to the left. So this point would exist at 1, 2 if it could, but it doesn't quite reach 1. Now this piece of the graph is your reciprocal function. If x is 1, y is 1, it's got a point right here. If x is 2, y is a half. If x is 3, y is a third. So it does this thing where it goes kind of like that. So as x gets larger, y is getting increasingly small as it heads towards 0. So you would have to say then in this case that the function definitely is not continuous at 1, or f of x is not continuous at x equals 1. And then it was asking you to state the type of discontinuity and whether the function is left or right continuous. Okay, before I answer those last two questions, are there questions about this and why the function's not continuous at 1? So I feel like as long as you can graph it, being able to eyeball continuity is pretty straightforward for most students. All right, so the type of discontinuity would be a jump discontinuity. Remember that a removable discontinuity is just this hole in your graph. So a removable would be a hole where the graph would keep going. So like if I had a situation where this line kept going, well then in that case, I would say that this discontinuity was removable. And remember that when we look at those functions, that would be an instance where you would be able to factor your function and cancel out the factor that caused the function to not be continuous there in the first place. So you'd get a hole in the graph, but it would keep going on both sides of the hole. It would be left and right, or it would not be left and right continuous, but it would be, the limit would exist from the left and from the right as you approach the point. You also had an infinite discontinuity, and an infinite discontinuity was when you had some sort of vertical asymptote and one or both of your left or right limits would be infinity in that case. In this case, you have a jump discontinuity, which happens a lot with piecewise functions because technically the graphs would be continuous on their own. The limits exist but are not equal. Whereas like for an infinite discontinuity, the left and right limits would not exist. And then the last question was asking you about whether the function was left or right continuous. So what you're looking for with left and right continuity is you're looking for the value of the limit to be equal to the function value. So you're asking, does the limit as x approaches 1 from the left of f of x equal f of 1? And does the limit as x approaches 1 from the right of f of x equal f of 1? So those would be the questions that you're asking yourself when you're trying to determine whether or not your function was left or right continuous. Now, in this case, when you're looking at x as it approaches 1 from the left, you're approaching on this linear piece of the graph. And as you approach 1, even though the limit exists, the limit is 2, but f of 1 actually, in this case, does not exist. So we would not be able to say that this is a situation where we have left continuity. But for right continuity, the limit as you approach 1 from the right is 1, because the y value is 1, and the function value at 1 is 1. So we would say 1 equals 1, therefore f of x is right continuous. I think all that's on your key, but I'm not 100% positive because I don't know which key I have here. Some kind of key. Okay, so that was 21. Any questions on 21 or that concept from number 21? Okay. So can we go over test 5 review number 12? Let's see. Okay. Yes, I'm actually really glad you asked me about this because there might be something on here I didn't want to be on here, but actually this one looks okay. Oh, you know what? This is like a kind of I didn't want it to be on here, but not that bad of a, and I didn't want it to be on here. But since it's on here, it's not a big deal. We're just going to use one of your properties to rewrite this one. Trying to remember where I gave you this property. Looking through my notes, but it has disappeared. want to say it was part of 5.4, even though this particular question was
It was 5.3, I think,
5.3. Okay.
because that's how I found it.
Okay. Okay, let's see. All right, so here's the deal. And I'm going to remind you, because I have your notes, I'm going to pull them up and show this one. So you're being asked to find the derivative using the FTC. So this is d dx of the integral from x to the fourth to 1 of the tangent of t dt. Now, your formula here, as soon as I start taking these apart, I'm just everything is going to get lost. Okay. So you had a formula stating that your derivative was equal to f of x, assuming that we were starting with a lower limit of a, where a was a real number, and going up to x, where x was a variable. And then we also had situations where instead of having x, we had some function of x, like u of x, and we worked with those. I did not actually give you anything that was like this. However, this is basically just going to be using that property that I gave you in 5.4. So it came after, and we used it a couple of times yesterday as well. So the deal is, because you have the upper limit as a and the lower limit as some function of x, you're going to have to switch those to get them to match our form. So you can rewrite this as the derivative of the negative integral from 1 to x to the fourth of the tangent of t dt. Because remember, if we make the integral negative, we can switch the upper and lower limits of integration. I think I was going to give you an example like this, and then I was just like, kind of want to be done with the part 1 of the FTC. And then maybe I forgot about it, or maybe just didn't think it was the best use of our time. Okay, but this does use a property, and it's a good idea to remind you of how to do these derivatives anyway, because it wasn't really a major focus for us. We can take this negative sign outside and bring it out in front of your derivative, and just write this as the negative derivative of the integral from 1 to x to the fourth of the tangent of t dt. And then we can treat this like we would have any other problem that we did finding these derivatives. So we'll let u be equal to x to the fourth, and then du dx is 4x cubed. So this will be where we use the chain rule when we actually go to apply the derivative, and we'll just kind of pop this onto the function. So we'll rewrite this then as the negative, because I have to keep the negative in front, and we'll keep our tangent, but the tangent, instead of being of t, will be of x to the fourth. And then we're going to multiply that by 4x cubed. So, I mean, technically this is okay, I guess. It doesn't look very clean. So you would want to rewrite this as negative 4x cubed tangent x to the fourth. So that was the trick with this one, just switching those limits. And it looks like, yeah, that's exactly what needed to be done here in your answer. It looks like you just didn't have the negative. So that's where that comes into play. So it's very important for us to recognize that if we don't have the lower limit being the real number and the upper limit being the function of x, that we need to switch those limits of integration so we have those in the correct order. And by applying a negative on the integral, we can do that. So yeah, so that, I guess I don't mind that so much that that one was on there. Because it kind of what we were able to combine two ideas there. All right. Questions on that one? Let's see what's in store for us next. Number 43 and 44 on the final review guide. I believe these were integration problems. Oh, optimization problems. Oh, 2 people asked. Oh, Alberto, when you said 43 and 44 on the review, did you mean the final review or the test 5 review? I don't know how many questions were on the test 5 review, so maybe there's...
It's in the final review.
Okay, so same ones then that
Yeah.
Cameron wanted. Okay, cool. Okay, so number 43. A rectangular storage container with an open top is said to have a volume of 10 meters cubed. The length of its base is twice the width. Let's see, so a rectangular storage container. Let's try to make this look halfway decent here. This is gonna look terrible. Let's see. So I could have left it like that. Why can't I draw a cube today? Okay. Something like this. You guys, my drawing is failing today. Absolutely failing. Okay. Kind of. The length of its base is twice the width. Okay. So if the length of the base is twice the width, we might want to say that this is the base, and you can just write here that it's twice the width and just say B equals 2W. If you're really stuck on using X and Y, fine. But I might just leave mine as B and W because that's how the problem was written. Okay, then we're given information about the material for the base, which costs $10 per square meter. Material for the sides costs $6 per square meter. Find the cost of materials for the cheapest of such containers. Okay, so we need a couple of different things here. First of all, a rectangular storage container with an open top. Okay, what information did I give you about the height of this storage container? The height of said container. I gave you nothing, so that's fine. We'll call it H. I'm trying to figure out the best place to label it. Let's do it here. Every other time I look at this drawing, it looks great, and then it looks terrible. Okay, so the volume. And by the way, if you're wondering, like, okay, now we have 3 variables, how are we going to possibly work our way through this? Remember that even though we have technically 3 variables, I gave you the width of the base. I gave you the base in terms of the width. So technically, the volume of the box is the base times the width times the height, which I gave you as 10 meters cubed. However, we know that the base is twice the width. So that means 2W times W times H is 10. And that means we have 2W squared H is 10. If you have questions so far, by the way, please jump in. The other equation we're going to write is for the cost. Let's see, material for the base costs $10 per square meter. So sometimes when I write these cost equations, I find it easier to write them out using units and then to cancel out what units I don't need. I just feel like it's easier to keep track of things. So this is for the base, and the base we know, and by the way, I know technically we have B, but we're going to want this written in terms of two variables, and we only are using W and H at this point. So when we're talking about the base, we're going to say that the base of the box is 2W times W. So that'll be the area of the base of the box if you're thinking about this in terms of surface area. So it's going to be 2W meters by W meters. And then that's where your meters squared comes in. And then the meters squared cancels out with meters times meter. And that leaves you with just cost. So this is just for your base. So let's see. The length of its base is twice the width. Material for the base costs. Yeah, I should have named BL, but who cares? I guess we're not using it anymore anyway. Material for the base costs $10 per square meter. Material for the sides costs $6 per square meter. So we're going to add that to the cost for the sides, which is $6 per meter squared. And each side of the box, oh, wait, you know what? I forgot. Oh, no, we only have one base because it's open top. Never mind. If we had a closed box, we'd have a base twice, but never mind, open top. We have 1, 2, 3, 4 sides of the box. So we have 4 sides total, and each side is going to be H meters by, actually, this is not a cube. So we're going to have 2 sides that are going to be the same and 2 sides that are going to be the same. So let's not use 4. This will be twice. And then we'll have 2 of these 2W times H. And this will be for 2 sides. And then the other 2 sides will be twice. So that'll be these 2 sides now, W times H. And then both of these will be in meters. I know now we're just using so many letters, but the meters are going to cancel. And then we can simplify. So this will be 2 sides, and this will be 2 sides. So this will be the 2 longer sides, and this will be the 2 shorter sides. And we'll simplify the cost equation. So it's just in terms of money now, it's cost. I'm going to drop the dollar signs. 10 times 2W times W, so that's 20W squared. And then we'll multiply the rest of these values together. We'll have 6 times 2 is 12, times 2 is 24, times 2 is 48. And then we'll have W squared times H squared for our cost there. I'm looking at my key. So I'm going through this, by the way. But everything looks different on the key. Oh, hold on. Sorry, I know why. It's because I multiplied this instead of adding them. All right. Where's my eraser? Eraser. All right. Well, $6 per meter squared. Let's focus first on, let's say we're focusing on this side. We'll highlight it here. Sorry about that. Okay, so this side is the same as this side. So we're talking about the shaded sides now. And each shaded side is going to be 2W long and H tall. And then these will both be in meters. So the meters still cancel. So this will be the cost. Let's see. For the material for the sides is $6 per square meter. So this will be the cost for the two longer sides. And then we'll add that to the $6 per meter squared. And then we'll add that to the cost for the two shorter sides. I don't want to shade these because then it'll be super confusing. If you want, we can just maybe do that to them. So that'll be like the two shorter sides. And these are going to be W wide and H tall. And that's in meters and meters, and then the meters again will cancel. Which makes more sense. We can't have a fourth dimension here for our box. Sorry about that. All right, so we have 20W squared plus, and then we'll have 12WH, and then plus 6WH. Oh, what am I still missing? 2W, WH, 18. How do I have 36 on here? I don't know. It's possible that my key is off, which is usually not the case. Usually the key is like heavily vetted. I don't know. You know what? I wonder if your key is not the one I'm looking at, and maybe I fixed the key. And I'm just trying to figure out, like, because now I'm thinking, like, maybe they were looking at this key and it didn't make sense to them. And now they're asking me about it, and maybe I'm looking at a different key than you are. So that should not be. Should not be. 40. There it is. Nope, your key looks the same as the one I'm staring at. Why do I have 4XY and 2XY? The 2XY makes sense. 2. Oh, I know why. I didn't multiply by the 2 sides. You guys, I'm falling apart over here. Falling apart. 2 longer sides, 2 shorter sides. I only included 1. All right, so we're going to have to multiply this by 2. So this was the length of 1 longer side. Here, how about this? We'll call this 1 longer side. And then it's got to get multiplied by 2. So if this is one of your longer sides, you have the cost times the length of the side times the height, and that gives you 1 of them. And then we're going to need 2 of them. So I'm going to multiply this by 2. So let's pop it in here somewhere. Multiply it by 2, and this will represent 2 of the longer sides. And then this one, again, needs to get multiplied by 2 because this was technically only 1, and we'll multiply it by 2. I'll leave that there. And that gives you the 2 shorter sides. The worst part is those 2's were actually there, and then when I erased it, they got lost. All right, so 6 times 2 times 2, that's 12, times 2 is 24 WH, and then 6 times 2 gives you 12 WH, and then you have the cost is 20W squared plus 36 WH. Okay. It's good. I just want to give you a minute to make sure you don't have questions on it before we continue, because it's the setup that's the hard part. And once you get here, substituting and taking the derivative is more straightforward. Okay. All right, so let's get everything written in terms of one variable. We're going to solve for the h. So let's see, going down here, we'll say that we have h equals 10 divided by 2w squared, which is 5 over w squared. And then substitute that into your cost equation. This is where we're trying to take that minimum cost. See, 20w squared plus 36w, and then h is 5 divided by w squared. And then simplify again. 36 times 5 is, I believe, 180. 180 over w is 180 w to the negative first power. And then we'll take the derivative. dc dw is 40w minus 180 w to the negative second power. If you'd like, you can pop this into the denominator as w squared. That's kind of what we were doing just because we were getting this into one fraction. In general, for a case like this, you don't need to worry about it. But if you want to be consistent and do the same thing all the time, then just do that. And then you can focus on letting your numerator be equal to 0, because you don't need to worry about your denominator being 0, because if w is 0, the width of your box is 0, then you don't have a box. So we'll have 40w cubed is 180. W cubed is 180 divided by 40. 18 divided by 4 is 9/2. And then W is going to be equal to the cubed root of 9/2 meters. Let's go back to your directions here. Find the cost of materials for the cheapest such container. So when you're talking about W, in that case, you are just talking about well, we're going to have to actually figure out then the cost for the sides. W is just going to be a dimension. So let's solve for H, and then to find the actual cost of the materials, you'll have to put this back into your cost equation. So we said that H was 5, there it is, 5 over W squared. So that's 5 divided by the cubed root of 9/2 squared. If you'd like, you can simplify this by just multiplying by another cubed root of 9/2. If you do that, you'll have 3 of them in the denominator. And if you have 3 of them, well, if you cube root a cube, you just get that quantity to pop back out. So it will just be 9/2 in the denominator, and then the cubed root of 9/2 in the numerator. Then you can simplify again and call that 10/9 times the cube root of 9/2. This will be your height. And what we really just need here is W and H, and we can put this back into your cost equation, and you can get an approximate value for the cost. And it's up to you where you want to do that. You might want to just do that here. Sorry if you can't see where here is. This equation maybe. And you'll get C equals 20W squared. And this is a cost, so you're going to have to end up rounding it off anyway, because it's going to be written in cents. So you might as well just get me a decimal approximation here for the cost. The cube root of 9/2 squared plus 36 times the cube root of 9/2 times 10/9 times the cube root of 9/2. And you should come up with approximately $163.54. Oh, yeah, that one was kind of a doozy, wasn't it? Just a lot going on in that one. I wouldn't put one that complicated on the final. It just combined a lot of different elements in one particular problem. Okay, and then the next one. The next one is about the Norman window. I believe you had one really similar to this on your homework from 4-7. I'm positive. Let's see. A Norman window has the shape of a rectangle surmounted by a semicircle. You know, I remember doing something really similar to this in the office hour. So if I did, the notes would be somewhere in the 4-7 office hour notes if you wanted to see something similar. What is this, number 44? Yes. A Norman window has the shape of a rectangle surmounted by a semicircle. the diameter of the semicircle is equal to twice the width of the rectangle. Now, if you want to call it W, fine. I kind of want to get back into X and Y because I prefer X and Y. Let's see. The diameter of the semicircle is equal to the width of the rectangle. So let's just say this is X and that's Y. Well, then this is also X. If the perimeter of the window is 30 feet, find the dimensions of the window such that the greatest possible amount of light is admitted. So we'll say that this is a question where we're going to maximize the area. You can think of it as surface area. We'll just think about it as area in this case. We have a number for perimeter. So right off the bat, we can go ahead and find the perimeter of this window. Now remember that if the diameter of your circle is X, then the radius is X over 2. So if you're thinking of your semicircle, the radius is 1/2 X in that case, just half that distance across. The circumference of a circle, and you have a geometry formula sheet, is 2 pi r. However, you don't have a full circle here, you only have a semicircle. So the circumference of a semicircle is just going to be pi r because you're only taking half of that. And then to get the perimeter for the rest of the window, we'll just add the remaining sides. The circumference, if you'll remember, is just the distance around a circle. So for the perimeter of the entire window, we know that for perimeter, if you want to start with the rectangle, that's fine. So you know that you have X plus 2Y plus, and it's possible, did I give you a figure here? No. Okay. So when we're talking about the perimeter of the window, we're only talking about the distance around. So technically this should probably just be a dashed line because I don't want you to think it's actually like a panel on the window itself. It's not included in the perimeter. And then we'll take the semicircle as pi r. Well, r, we already said, was 1/2 X. So we have 1/2 X times pi. And that's equal to 30. Now we'll write an equation for the area. If you have questions, please ask. Or if you see me do anything weird, which has been known to happen, especially this evening. For the area, we're going to write the area as, well, the area for the rectangle is just going to be xy. So this will be for your rectangle. And you're going to add that to the area for the semicircle. So for the area of a circle, we have pi r squared. For the area of a semicircle, we have 1/2 pi r squared. So the area in our case is 1/2 times pi times, we said the radius was 1/2 X squared. So that's your R in this case. And this is for the area of the semicircle. And then we'll simplify that equation. xy plus 1/2 squared is 1/4. Times that by 1/2 and you get 1/8 pi x squared. So now we're going to have to go through and solve for a variable using the perimeter equation. Now notice that in your area equation, you have an x appearing in two different terms. You only have a y appearing in one term, and it's only to the first power. So if I were you, I would sub out the y. And I know that you're looking at this and it seems like, that seems hard. Well, actually, for the x, it's harder because when you sub out the x, you're going to have to factor, do all kinds of crazy stuff. So let's go ahead and solve the perimeter equation for y. So to do that, we'll get 2y is 30 minus x minus 1/2 pi x. And then just y by itself, you're going to divide every term by 2. And you'll get 15 minus 1/2 x minus 1/4 pi x. And then we're going to plug that in for y in your area equation. So for the area, and this is what we're trying to maximize, we have x times y. So we're going to sub in y as 15 minus 1/2 x minus 1/4 pi x. So that would be our x times y plus 1/8 pi x squared. And we're going to simplify. Since we're going to have to take the derivative, I don't want to have to worry about using the product rule if I don't have to. So I'm going to just simplify, maybe combine some like terms, maybe. Notice that you have 3 different x squared terms. You might want to combine them. You might not want to combine them. It doesn't matter. Whatever you want to do. I'm going to leave mine separate because otherwise I'm just going to have things factored out of it that look funny. So I'm just going to leave it. Just take the derivative of each term on its own. dA dx is 15 minus 2 times 1/2 is 1 x. 2 times 1/4 is 1/2 pi x. 2 times 1/8 is 1/4 pi x. Now we're going to set this equal to 0 and solve. When we do that, what was I going to say? Oh yeah, we're just going to have to do a little bit of factoring to solve for x in this case. Minus x minus, okay. Which is fine. And if you want to combine these here, fine. If you don't, also fine. They're going to get combined at some point anyway. So we're going to set this equal to 0. We're going to solve for the values of x where this occurs. So I'm going to move the 15 over to the other side, and then I'm going to factor out the x and combine all the coefficients. The order in which you do that does not matter to me. Let's see. I'm just going to leave the x's on the left. Negative x. I'm going to do this in 2 steps. And this is like contrary to what I would normally do, which would be to leave everything positive if I can. Let's go ahead and take out the x's to solve for x. I'm going to take out a negative x, I guess. Ugh. That's no good either. That's fine. We'll just leave it. It's fine. And then you'll have 1 plus, so I'm taking a negative out. So when I factor that out, I'll have 1/2 pi minus 1/4 pi equals negative 15. And then we'll have x equals, I'm going to divide both sides by negative 1. So I'm just going to call it positive 15. And then 1 1/2 minus 1/4 is 1/4. So just dividing both sides by, I feel like I should have included one more step here, but just combining these two terms together gives you that 1/4 pi. And then you have 1 plus 1/4 pi in your denominator when you divide it out. If you would like, you can rewrite that by getting rid of the complex fraction, but it's really not going to look much better. You can multiply every term by 4, and you'll get 60 divided by 4 plus pi. Wait, this number looks really familiar. I wonder if this is the same problem that I put on that was from your homework. That would be really bizarre, though. Yes, it's possible. There are only so many Norman window problems you can do in this world. It's true. All right, so that's your x. Your y is going to be kind of a pain. Sorry to have to tell you that. Did I ask you a specific question? I'm always hoping that maybe I don't have to answer the other half. No, find the dimensions. That means find x and y. Okay. Remember we had y as being 15 minus 1/2 x minus 1/4 pi x. So 15 minus 1/2 x minus 1/4 pi x. That's going to give you y. This was in feet, right? Yes. Just verifying. And this is not going to simplify really nicely for you. You can divide by 2 here and just leave the 4 plus pi in the denominator. You can divide by 4 here and just leave that as minus 15 pi divided by 4 plus pi. The nice thing about that is if you do that, each one of these denominators will have a 4 plus pi. So at that point, you could at least combine the numerators together. You could say that you have 15 minus, but be careful when you do that because you're subtracting off the whole thing. And if you're subtracting off the whole thing, this will become plus 15 pi because that minus sign will eventually be distributed. So if you're not comfortable, leave it there. If you're okay with it, put it here. And there's even more stuff that you could do to this, which I did, I believe, on your key. Yes, I kind of showed how you would keep simplifying this by giving this the same denominator of 4 plus pi and simplifying it down. If you did that on your key, that's fine. It would be simplified. Honestly, at this point, I would be happy if you got me this. I'd probably still be thrilled if you gave me that. If I said write your answer as one term because I knew what the answer would be and I wanted you to simplify it all the way, I would specify. Morgan, what is your question?
How did you get, like I'm looking at like the first problem that you had boxed, how did you get 15 pi over 4 plus pi?
15. Here?
Yeah.
Oh, so with this one, I just took 60 and divided it by 4 to get the 15. And then I just kept the pi in the numerator. So I just canceled out here. 4 divided by 4 is 1. 60 divided by 4 is 15. And then the pi just carried over. And I did the same thing here just by dividing 60 by 2. Does that answer your question, Morgan?
Yeah, thank you.
You're welcome. Other questions? Did we answer the question? Find the dimensions. Yeah, so these would technically be the dimensions of the window. If you want the fully simplified version of y, it is on your key as 30 divided by 4 plus pi. But to get that, you would have to get the common denominator 4 plus y in both terms, which is not like a super hard thing to do. It's just, unless I specified that I wanted your answer to be written as one term, it's really not something I would want you to be spending a ton of time on. Although it is kind of driving me crazy that it's 2 terms and I didn't put it in parentheses. Because the feet applies to the whole thing. Okay. All right, good. So we knocked out those 2 problems. Let's see what's next. Number 13 on the test 5 review. So this was another FTC problem, finding the derivative. I was at the pool with my kids today. I told my friend, like, oh, I don't normally have to teach Tuesday nights, but I'm teaching tonight, and I kind of explained the situation. She was like, oh, well, if it's an optional question and answer session, maybe nobody will show up and you can go do something else. And I was like, first of all, they will show up. I know this class. They're very good students. And you did. You showed up, which always makes me happy. And then I was like, also, I don't want to go do something else. I'd rather do this tonight because I was with the kids all day long. So I'm really happy doing this right now. Number 13. I love them. It's a lot on a daily basis. Test 5. Review. Number 13. MTH. My husband is getting a babysitter Thursday night while you guys are taking your final exam. He's going out and having a celebratory dinner with his friends. And I asked him, like, what is it that you're celebrating? I don't understand. What do you mean celebratory dinner? He's like, oh, just you being done with work and I don't have to watch the kids every night by myself anymore. I tell you, these poor children. All right, so we have the derivative with respect to x. We're going from 4 to 6 square root x t divided by t squared plus 1 dt. We're being asked to find the derivative using the FTC. All right. So you're going to check 2 things. First of all, make sure that one of your limits of integration is a constant. The other thing you're going to check is just making sure that it's the lower limit of integration that's the constant. If it isn't, you're going to have to multiply by a negative and switch those limits. So before you get really started on this one, go ahead and set up your u. Since you're going to have to take the derivative, just write it as 6 times x to the 1/2 power. Since you're going to take du dx, you want it written like that. So go ahead and take the derivative, and you'll get 3 divided by the square root of x. Now this is what you're going to chain on. Oh, did someone have a question?
Yeah, where'd you get the 6 from?
Oh, the 6 came from here. Yours had a 6, right? Oh, I wonder if I might have pulled this off someone else's.
Mine has a 4, but everything else is the same. It's 4.
Oh, it has a 4 root x?
Yes.
Oh, okay. So the one I pulled up, it must have been on someone else's assignment, had a 6. So
mine.
What's that? Oh, maybe it was Cameron's.
Yeah.
It might have been Cameron's, and I was like, oh look, I still have the assignment open, so I didn't take like the time to go back and find Burfin's. Sorry, Burfin. But if it went from 4 to 4 root x, was that? Well, I guess technically the lower constant doesn't even matter. But if it was 4 root x, then your derivative would just be 2 over the square root of x, because you'll be doing 4 times 1/2, and you'll just get 2 over the square root of x. I know I've spoiled you guys with pulling up your exact assignment, and now I screwed it up. That's okay. All right. When you take the derivative, you are going to evaluate the function. Everywhere you see t, you're going to substitute that upper limit of integration. And then you're going to multiply by the derivative of the inside function. And you're going to simplify. Okay, so the square root of x's in the numerator and denominator will cancel. The 6 times 3 leaves you with 18. And the denominator, 6 squared is 36. The square root of x squared is just x. Now, whatever you do, don't cancel between the 18 and the 36. You cannot, because you cannot factor a 36 out of here. If you can't factor it, you can't cancel it. So this is done. Don't try to take it any further. It's done.
How'd you get 36? I'm kind of confused with this one.
Oh, so 6 times the square root of x is being squared. So when you're squaring it out, you're just multiplying it by itself.
Okay.
And that's where you get the 36x. Yours will be different. Yours will be like, I don't know.
16, I think.
Yeah, you had 4 root x. So if you have 4 root x times 4 root x, yeah, you'll have 16x. And your numerator will be different too.
Thank you.
8. You're
Yep.
welcome. 8 and 16, and don't cancel between the 8 and the 16. Okay. Let's see what else. Homework 5.5, indefinite. Oh no, wait. So this is, Isabella, were numbers 6 and 11 from the definite integrals portion?
Yeah.
Okay. And then 16 and 18 were from the indefinite portion.
Yes.
I know we have to get even more specific on the 5.5 requests. All right, let's see. I'm going to get out of this review assignment. There's Isabella. 5.5 definite. Numbers 6 and 11. So number 6 is the integral from 0 to 1 of 3x divided by 1 plus x to the 4th dx. I'm smiling because this is one of those ones that's trickier to figure out. I don't know why that made me smile. Because it's instructive, I guess. Okay, so this is one of those problems where you have 2 options and you have 2 different ways that you might approach it. One of the ways that you might approach this is just to let your denominator be u. However, if you did that, you would let, I want to say try, you would let u be equal to 1 plus x to the 4th, and du would be 4x cubed dx. Well, you don't have the x cubed, so that's not going to work for you in this case. Think about the fact that you have a constant plus a value squared, specifically 1 plus a value squared. Now you're wondering, like, why is she saying I have a value squared? Clearly it's to the 4th. Well, remember, first of all, I'm going to move this 3 to the outside. I'm going to rewrite this to make it look a little bit clearer. X to the 4th can be rewritten as x squared squared. That's the trick with this one, if you want to think of it as a trick. This is really an inverse tangent in disguise. So keep an eye out for something like that. If you had here like 3x cubed in the numerator, absolutely I would do a u substitution, a standard u substitution. This would work where you were just doing du over u with some sort of constant multiple. But it all has to do with how many powers of x you have. And in this case, you only have one. And if you're still thinking like, well, how does that help us here? Well, think about the fact that if you were to look at this as an inverse tangent, and I'm going to remind you again what that looks like, du over 1 plus u squared, the u value would actually be x squared because that's what's being squared. If you're taking u squared, then in this case, u wouldn't be x, it would be x squared. And this is where you're going to get that dx to pop out so nicely for you. So du is 2x dx, and you have an x dx. So all you need to do is just divide that 2 out. You should also switch your upper and lower limits of integration, since we're about to rewrite this. If x equals 1 and x equals 0, I know that u is going to be 1 squared, which is 1, and 0 squared, which is 0. So that worked out nicely. I wonder if some of those iterated. It looks like everyone's are from 0 to 1. The only thing that iterated in this problem was the 3. Everything else was the same. Also, bear in mind, as you're looking at this particular example, this could have been an even more disguise. This could have been written with something other than a 1 here. It could have been written with a constant multiple on the x to the 4th. Any of these numbers or constant multiples could have been different. The key here, what you're really looking at, is just the variables and their exponents. Any other values that happen to be multiplied by those quantities aren't going to affect your solution process. If this wasn't a 1, you could easily make it a 1 by dividing every term by whatever that number was. And you could always write this as a quantity squared, no matter what. So it could be even more disguised than it is. Keep that in mind. Okay, so we're still going from 0 to 1. I have a 3 still in front. I'm even going to write u equals 0 to u equals 1 because I want to make it clear that we actually checked them and it's just a coincidence that they're the same in this case. And it wasn't just a mistake that I erroneously put x limits on a u integral. And then I'll have 1/2 du over 1 plus u squared. If you want to take the 1/2 out right now, that's fine too. So I have 3/2 times the inverse tangent of u, and that is going from 0 to 1. And hopefully we're getting really familiar with our tangent values after doing what seems like so many of these integrals. Inverse tangent 1 minus inverse tangent 0. Technically, if you left this on your test, you would still lose points because these are values that you can easily evaluate. If it was inverse tangent 3, yeah, there's nothing you can do there. I don't want an approximate decimal. But in this case, these are exact values. So please make sure that you enter them. I mean, yes, you would technically get points for just showing me this, but you wouldn't get all the points. So the inverse tangent of 1 is pi over 4. The inverse tangent of 0 is 0. And you would get 3 pi over 8. The other one was number 11. Oh, this is another one that makes me so happy. Okay. Before I do that, questions on number 6, lingering questions? So anyone else who did this problem, the only thing that's going to be different is this 3. It's possible that it could have been something that was had a common factor with 8, but I doubt it. I shouldn't be telling you that. One, 2, 3, 4, 5, 6, 7, So this was 5-5 part 2, number 11. And this one is the integral of x plus 7 divided by x squared plus 1 dx. Okay, so I want you to get really familiar with seeing these, but this is very, 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 very similar to the last example I did in class yesterday. And I believe that might have been an inverse sine for your last term. Double check. It's like one of my favorite examples of all time. You'd think I would have remembered it. Yes, it was an inverse sine. So this is the one where it looks like it could be two different things. However, this one looks like it could be an inverse tangent because you have 1 plus x squared in the denominator. However, if u is equal to x, then du is equal to dx, and you can't fabricate this x out of nowhere. So if you tried to do a standard u substitution, you would let the denominator be u, and you'd get u is 2x dx, and that's where you run into the problem that we encountered yesterday in the last class example that we did. What was that, number 26, I think? I feel like I want to write that it's similar to I don't know. 26. Similar to class example number 26. Okay, so even if you divided out the 2, that's good. We're still going to need to do that. But the only thing that you can come up with here is an x dx. You cannot add anything onto that to create x plus 7 dx. So if you tried to say this, it's so weird when students do this. You cannot do that. I don't even know how to make that look normal. You can't do that. So the trick here is to split into 2 integrals. One of them can use the x divided by the denominator, and the other one is going to use the 7. And I'm just going to pull the 7 out as a constant multiple, just because I know that this right here by itself is a straight up inverse tangent of x. Everything is exactly in the right form. So the last thing I need is a 7 that's thrown a wrench into my plans. So I'm just going to yank it out. Okay. But the nice thing is now we already have so much of the work done for this problem, and it's an indefinite integral. We don't even have to worry about switching any limits of integration. This is our u substitution, and this is our inverse tangent. Technically, we don't even have to do a u substitution because we just have x squared, so you can even just say that's inverse tangent x, call it a day. Okay, so for the first term, we have an x dx that we're subbing out for 1/2 du. So we'll have 1/2 du over u. And then for the second one, you can just write this as 7 times the inverse tangent of x plus c. And then we'll work on the u substitution and finish this one out. So this one is in the form of a natural log. Remember, the derivative of ln u is 1 over u. So we'll integrate this as 1/2 times the natural log of the absolute value of u. And of course, you could just kind of combine all this at the end instead of rewriting it with each step. And then this will be 1/2 times the natural log of the absolute value of, if you don't remember what u was, it was x squared plus 1. Now, I want to mention right here that this is a special case of u being positive all the time. If you take a value and square it, it's going to be positive. Then if you add 1 to it, it's still going to be positive. U is going to be positive no matter what you do to it. Because of that, you don't have to include the absolute value bars. It's going to be positive no matter what. Now, officially, if you do put the absolute value bars on it, it's not wrong. It's still going to be positive. It's not going to be restricting your answer. It just doesn't make sense to force it to be positive when it's going to be positive anyway. X squared plus 1 can't be a negative quantity. It just can't be. So this one doesn't require the bars. We can say x squared plus 1 will always be positive. So the absolute value bars are not necessary. And then the other was off of 5.5 part 1. Look at that and see if you have questions while I pull this one up. Numbers 16 and 18. And this was a longer assignment. Okay. Wonderful. Okay, so these are both going to be similar types. $16 is the integral of 4 dx divided by x squared plus 64. And I'm glad we're doing this one just because the last couple inverse trig problems we did tonight were a little bit more straightforward, or I don't want to say easy, but you didn't have to do as much work to them because the ones we looked at tonight had 1s in them. This one has a 64 in it. This is definitely an inverse tangent form. And we know that because u in this case is going to be, well, if you were starting it out now, we can't really call it u yet because we don't have this as a 1, but it would be something x, and its derivative would be a constant. And we only have a constant in the numerator. If you tried to let the denominator be u, du would be 2x, and you don't have an x up here in the numerator. So this is definitely an inverse tangent form. I will remind you again that this is going to be du over 1 plus u squared is inverse tangent u plus c. And I did a couple like this on the first 5.5 assignment, but these are definitely trickier. This one hopefully will be a little more straightforward because it looks like we're dealing with some perfect squares here. If you want to take it out of the integral, fine. I'm just going to go ahead and work inside the integral for right now. So everywhere I see, not everywhere I see, I'm going to divide each term by 64, and that's because I need this to be a 1. I need this to be a 1 so I can match this form where I have 1 plus u squared in the denominator, and that's going to affect the value of u. Now, you're right, it's not going to change a whole lot, but it's going to change our constant multiples. So I'm going to take 4 and divide it by 64. And I'm going to take x squared and divide it by 64, and take 64 and divide it by 64. But nothing has really changed other than we've just shown every term being divided by 64. If you'd like, you don't have to. You can move this as a constant multiple in front of the fraction. I might do that. You might want to put it back later. It's up to you. Like I said, it distracts me, so I like to get rid of it. 4 goes into 64 16 times. So we'll write that as 1/16 dx divided by, and the first term, we need to write this as a quantity squared. If I want to write 64 as a quantity squared, then I need to take its square root. The square root of 64 is 8. So I can write x squared over 64 as x over 8 quantity squared. And then 64 over 64 is 1. So we had to do a little bit of work here, nothing too crazy, but definitely a couple different things needed to be done to really get this into the form that we needed. Please ask questions if you have them. The worst part about virtual office hours is I feel like it's just so much harder for students to answer questions. Where I used to feel like I would guide you through a solution process, now I just feel like I'm doing problems for you, which students like, but I don't know. Not the same. I found out that in the fall, even for the hybrid and in-person classes, the office hours are required to be virtual. Can you believe that? Oh. Yes, it's true. All right, we're going to let u be 1/8 x. Like if you wanted to, you could not hold in-person office hours for your in-person class. All right, so we're trying to match this form. I have the 1, so I'm letting u be 1/8 x. du is 1/8 dx. And then 8 du is dx. Okay, so this is going to be 1/16 times the integral of 8 du divided by u squared plus 1 or 1 plus u squared, whatever you need to do there. And 8 over 16 is 1/2. So this is just going to be 1/2 inverse tangent u plus c. You know, it's always so bizarre when you get to the end of these because you feel like you did all this work and the only thing that changes is this constant multiple. I mean, I guess technically the u quantity, you have to figure that out too, but there's not like a whole lot that's really happening here. Sub back in for x. And this was number 18. Again, this is looking like an inverse trig form, and it is because you'd be thinking that u is something x, you don't know what yet, but then du would be a constant. If you had an x in the numerator, this would be a u substitution. U would be 16 minus x squared. Du would be negative 2x dx, but you don't have an x in your numerator. So you know that this is going to be in the form of an inverse sign. I will remind you of what that is. It's du divided by the square root of 1 minus u squared. We don't do a whole lot of inverse secants. You might have seen like one of them on your homework, maybe. I don't even know. Maybe I pulled it off. They're slightly trickier, but meh, you don't really see them a whole ton. All right, so again, I'm in a situation where I need the constant in the denominator to be a 1, and it's not. But we're going to have to be a little more careful here because we have a radical that's involved. So when I rewrite this, under the radical, I'm going to divide each term by 16. Now, if I divide it under the radical by 16, I need to do the same thing in the numerator. Okay, sometimes I have 2 dx's. I go overboard. I don't know what's worse, no dx's or 2 of them. Okay, so when you divide by 16, it has to be under the radical in the denominator to get you a 1 in the radical, but then you have to remember that it was under the radical, so that has to be done also in the numerator. But the nice thing is you can yank that out as 11/4 times the integral of dx divided by the square root of 1 minus. And then if you want to write 16 as a quantity squared, take its square root and you get x over 4 quantity squared. X over 4 times x over 4 gets you x squared over 16. And now you are all set to do your u substitution here for your inverse sign. You're going to let u be 1/4 x, and du is 1/4 dx. 4 du is dx. And I was saying yesterday, and since it was in class, I didn't do it, but if you want, when you get 1/4 dx, you technically have 11/4 dx. So if you didn't want to have to do anything here, you could just multiply both sides by 11. And then you could say, well, okay, I already have 11/4 dx, so we'll call that 11 du. It's not a big deal. It just means that you don't have to do any canceling, like multiplying and dividing. But I mean, it's up to you what your comfort level is. Okay, so that will be your 11/4 dx will be your du, 11 du, sorry. So we'll have 11 times the integral of du divided by the square root of 1 minus u squared. And then you'll integrate. You'll say that this is 11 times the inverse sine of u plus c, and then back substitute for x. 11 times the inverse sine of x over 4 plus c. All right, that's the last question I have in the chat, but I still have like 12 more minutes in case you have more questions. Morgan, yes, what's your question?
This is more like a general question for like the test.
Yes.
Are you gonna make us use the back substitute for x, or can we just like change the upper and lower limits to u and then do it that way? Like, is there a specific way you want it?
No, as long as you do it right, whichever method you choose is fine. So if you want to switch your upper and lower limits, fine. If you want to back substitute and use x limits, fine. Just don't do both. Don't switch to u limits and then back substitute for x. I've seen too many students do that. So just make sure if you're using u limits, you have a u integral, and vice versa. I can't tell you how many times on a test I've circled like the dx and I've circled the upper and lower limits of integration and said, you know, commented on there, you use u limits with an x integral, or vice versa. You use x limits with a u integral. The variables must match. I mean, I should probably copy paste that right now because I feel like it's going to be commented on these exams. I used to write in pen and then my pen would run out of ink, but now I to grade everything on D2L. It's awful. I wish I had like a giant stack of tests and I could go through and grade them the way I used to. That'd be really nice. Yes, such is life. But yeah, to answer your question, you choose your method. Either one is valid. I will not force you to change your upper and lower limits. This test, I feel like it's definitely going to be shorter than your last test. Partly, I'm trying to make it even shorter than normal, just because you have a test tomorrow and then you have a final Thursday, and I have to grade all that stuff. So I don't want to be like tearing my hair out, living in misery. I don't want to do that. So I want the test to be good. They're so much easier to grade when they're good and when they're shorter. But you know, it still needs to test your knowledge. So I'm going to choose wisely and make sure I include, you know, all the topics that we covered, but I don't want to go too far overboard because I have to grade them. Your final exam will be about the same length as a normal test, because it has to be, because you have to be able to take it in 2 hours and whatever it is, 2 hours and 20 minutes. Technically, it's supposed to be a 2-hour final, but I'm not going to cut you off at 2 hours. If our class goes on for 2 hours and 20 minutes, it seems really silly to be like, okay, it's 8 o'clock, you're done. And I don't know. So I like to give you the full time. Some people will be done early. I don't know when grades are due. People always ask me, but no one's actually asked me that. If you don't have questions, I might check real quick. I usually get an email telling me the grades are due because they have oh, I know what it is. Just because they have students who need to graduate and they can't graduate without their test scores, without their class grades entered. But maybe they never sent me an email. So many emails come through and sometimes I lose track of things. But I don't see one. Usually the way the grades work, and I feel like in summer everything has to be done even sooner, is that grades are due the Monday after finals. But maybe in summer it's longer because there are different sessions. But I'll check. I'm sure they'll send me an email in the next day or two just to remind me. If not, obviously I'll have to check. But the grades might be due Monday. They might be due a week from Monday because people have different start dates. And I think our class started a week earlier than some of the other session twos. I'm not positive. But I'm going to get them graded early because I have things to do during my 3-week time off, and I don't want to have them sitting around taunting me. Yes, Cameron?
Okay, so for the definite and indefinite integrals, for the indefinite integrals, is that when you add the plus c because it doesn't have the going from like 1 to 4 or something like that?
Yes.
Okay.
Yeah, so if you don't see upper and lower limits of integration, there's nothing there. It's an indefinite, and you would add the plus c there. And if you do have, you know what they look like. Yeah, if you do have the upper and lower limits, then that's when you don't use it. You just get a number instead of some function of x plus c.
Okay.
Other questions? Morgan, yes, go ahead.
This goes back to like the grading. But if we do need like our grades early for like classes or something like that, should we let you know, or?
I can only get them done so fast, but you can let me know if there's a specific date.
Okay.
Yeah, you can let me know.
Okay.
it's like I said, I mean, I have a feeling I'll have them done by Monday regardless, just because I want to just get it done. I mean, I still want to grade them responsibly, but I also just want to be done grading them because it's a lot of grading. And this is a big class. A lot of times in a Calc 1 class, I'm down to like 12 students by this point, and there's still like 25 of you. So it just makes it a lot to grade. I don't know what happens. It's like a Calc 1 thing. Every semester, it's like 11 students at the end. Every single time I teach it. Not in the summer, though. In the summer, it's always still full at the end. And Calc 2 is always still pretty full at the end, regardless of the semester. I can't figure it out. I wonder if sometimes maybe students aren't ready for Calc 1, and that's why, like, maybe the summer students are just kind of like really motivated to be done with it. I don't know. By the time you hit Calc 2, you've kind of been through the ringer maybe, so you are like more prepared. Because I think sometimes Calc 1 can hit students like a shock. It's just my opinion. So you'll have for the final exam just the whole class period. So 2 hours and 20 minutes. And that should be ample.
Was it 30 questions?
For your final exam, I have not finished writing it yet.
Okay.
So that's a really good question. Let's see. I think I had a previous final sitting around here somewhere. 30 seems like a lot, but maybe not. Okay, I could have sworn I had a previous final exam sitting here for the longest time. Now I can't find it. Maybe I never had it to begin with. Don't know. It'll be like page-wise, very at least comparable to one of your regular exams. Oh, I bet you it's in my Google Drive. Maybe. Maybe not. Let's see. Oh, there it is. It looks like they're normally maybe like 20 to 25 questions. Yeah, so going back to limits. So obviously a lot shorter than like the final review guide that I gave you, but still, like I said, there are just going to be more types of problems that you're going to see in your final review guide, whereas I can't obviously put that much stuff on a final exam. So your final exam is going to be pretty similar to like a subset of the final review. I mean, I cannot guarantee that it is exactly like a subset, but I mean, pretty much all the topics were covered. But if I were you to review for your final exam, I would definitely go through the final review guide, but also go through your previous tests and go through the keys for those, which I'm sure most of you know are on D2L under test keys. Just kind of go through those and just make sure there's no concept that you might have missed that seemed like, oh, wow, I didn't remember seeing this on the final review. I should probably look this over kind of thing. If you didn't see it on a previous chapter exam and you didn't see it on the final review, you're not going to see it on the final. I mean, I'm not going to throw something on there that wasn't even key enough to be put on a chapter test. I mean, I'm talking like the most essential concepts for the final exam. Nothing too niche. Yeah, I mean, when you think about a final exam, it's just really an indicator of like, is this person, like, do they have a solid enough standing in Calc 1 that they would be successful in Calc 2, kind of a thing. And that's kind of what I think about when I put the exam together. Because Calc 2 is a lot harder than Calc 1. Every once in a while, you get a student who says that's not true. And I guess for everybody, it's different. I thought that Calc 2 was the hardest of all the calcs. Some students will insist that Calc 3 is the hardest. I think it depends on your teacher. Calc 3 is more formulas, but definitely it's a lot more abstract. Calc 2, you kind of have to come up with a lot more stuff on your own. All right, any other questions? Okay, well, I'm gonna come on tomorrow. You're welcome, you too. I'll be on tomorrow. Good night, Ria. Probably at 5:30. I feel like we answered a lot of questions tonight, and I think there were only like 12 questions from the homework I assigned yesterday, so there's not like too much extra. I might try to make it on a little bit earlier just because I do have to, you know, go through the looking at people's workspaces thing, so I want to make sure we save some time for that. But definitely email me if anything comes up before the test tomorrow. Usually I answer a lot of emails around lunchtime. If it's like 3 p.m., then I might not get to it until the office hour. But if it's, you know, lunchtime, do that usually. What will I do during lunchtime for the next 3 weeks when our class gets out? I'm just going to have to like veg out and hang out to the Curious George. All right, you guys. Well, like I said, email me if anything comes up, and I'll see you tomorrow. All right.
Thank you. Good night.
Good night.
Thank you. Good night.
Yep, good night.